Now we will consider in detail what is a basic function block in IEC 61499 architecture. So, basic function block is a main component model to implement different kinds of functionality. The functionality is organized into algorithms. So algorithms written in different programming languages operate over internal variables. So internal variables can be encapsulated only into basic function blocks. You cannot declare variables on the level of application or system configuration. The only place where variables can be declared is in internal variables of basic function block. So you should remember that there are no global variables whatsoever in IEC 61499. And that is done with a purpose. And the purpose is, this is a language for programming distributed systems. In distributed system, it's impossible to organize in a vendor-independent way efficient handling of global variables. That is why a programmer has to declare variables in basic function blocks and explicitly share them via event and data connections between the blocks. So the algorithms are shared internal variables of the same block. So those variables that are declared on the level of function block can be used by all algorithms inside that block. And there is an execution control chart that is a state machine describing how the function block reacts on arrival of input events and how it calls algorithms and what happens after algorithm is executed. So all these algorithms are connected with each other using execution control chart. The algorithms can be programmed actually in any programming language. So the standard does not limit the choice of languages. In particular, standard refers to IEC 61131 languages as obvious opportunity to program algorithms, but that's not the only one. So in principle, tools can support any programming language inside algorithms. So let's consider a very simple example, a basic function block that calculates x squared minus y squared and outputs it as an output variable. So this will be real input variables x and y. So you see here this input variables x and y, which the function block takes, and it can sample those variables on arrival of the input event rec. So when this input event rec activates the function block, these two variables x and y are sampled, and then this calculation of x squared minus y squared is done. Then output event C and F is emitted, and with that output event, the associated output variable is made available outside the function block. Okay, so I will explain you later what init and init-o inputs and output needed for. But now let's focus on the main functionality, which is calculation of this output variable. So inside this function block, its overall execution control is defined by execution control chart. In this particular case, it consists of three states. The start state, where the function block is initially at the startup, and then at arrival of init input event, it goes into the init state, executes algorithm alg1 that is part of the action associated with this state, and having executed alg1, it emits init-o event, and then it returns back to start state, because this transition condition on the transition link between init and start state is always true, as indicated by 1. 1 means always true. So then if rec event arrives at the input rec of this function block, then it jumps from the start state onto rec state, executes algorithm alg2, and emits event cnf2. And this is the main function of this block. So the calculation of out variable will be located here in this alg2 algorithm. So the execution control chart consists of state transitions, which are arrows between the states. These state transitions have conditions. This condition, for example, of this state transition is rec, meaning that when event rec activates this function block, this variable rec is true. So that's why the state machine can jump from state start to state rec. So then it has actions. Action is a combination of algorithm call and event output, like this action, alg2 and cnf. So each state can have many associated actions. In this particular case, each state, two of the states, rec and init, have only one associated action, but it's not a limitation of the standard. So let's now see how execution control chart works in detail. So when function block is in the start state, if init event is triggered, then the function block will jump into the init state. Then it will execute algorithm 1 and emit init-o event. And then state will change to the start state. And then when function block in the start state and the rec event is triggered, algorithm alg2 will be executed. CNF event is triggered at the output, and state will change again to the start state. So each state can have, as I said, one or more actions associated with that, and an action may have an algorithm call and an output event emission, or it can have both, not necessarily. So it could be only algorithm and no output event, could be only output event and no algorithm. And in this case, as you can see, we have a little bit modified state machine execution control chart for the same block. We omitted the initialization part, and we have algorithm alg2 that is written in a language structure text, as it is defined in the start, in the initial line of this code. So it says that algorithm is an ST language, and it calculates output as a multiplication of x minus y and x plus y, which is x squared minus y squared. Okay, so transition conditions. Those conditions that are attached to the arrows, the transition arrows between states, they are called transition conditions. And these transition conditions can be only of the following format. It could be constant true, always true. It could have event input name, only one event input name, or it could be a Boolean expression over data, over for example, internal variables or input variables or output variables. Or it could have this following format: event input and then in the brackets Boolean expression over data. So only these four options exist for how transition condition can look like. There cannot be a transition condition that includes two names of two input events or more than that. So for example, the correct syntax of transition condition, just one event name, input event rec, or this long expression over data, that is Boolean expression, so it has to have logical result 0, 1, or false and true, or this form where there is an input event and Boolean expression over data, as it is indicated in the last line. So, how does execution control of a basic function block work? At the initial, before the event, any event arrives, all input variable values relevant to input event have to be made available. So it's indicated by number 1 here. So they have already calculated by the function blocks which provide these events, which provide this data, sorry. And then the input event occurs and it's associated with this data. So by that, execution control function of the function block is triggered. The execution control function evaluates the execution control chart, and by evaluating the execution control chart, it finds which transition condition is currently true, and if any of this is true, then it makes a transition to a new state and selects first algorithm for execution and notifies the scheduling function of that particular resource where function block is executed to schedule this algorithm for execution. So then algorithm execution begins, and algorithm completes calculation of values for the output variables, and that makes this data ready for being provided to the outside of the function block. And then it notifies the scheduling function of the resource that its execution is terminated. So the scheduling function again gives control back to execution control chart and tries to find if there are any more conditions that can be evaluated to true on the transitions of that function block. So basically outgoing arrows from the state where the function block is now. So, and this process repeats over and over again until there are no transitions that can be evaluated to true. And then the execution control function lets the event to be emitted at the output, and the data at the time become available, the associated data become available. Okay, so again, an example of some hypothetical basic function block that has execution control chart composed of 4 states, and we assume that it has several modes of operation. First of all, it has initialization. Initialization is assumed as a required function of the function block at at the startup or the power up of the device, the first thing to be done is initialization, which will set all internal variables and output variables to some initial value. And then there are two modes of operation, the main mode of operation and the shutdown. And now you will see what is the purpose of this Boolean input QI, and so it is used often. It's used to indicate, it's used as a qualifier to allow for initialization and deinitialization of a function block. So in case if QI is equal to true or 1, that is interpreted as the function block is initialized, and if event init arrives and QI is equal to false or 0, then it can be interpreted as a deinitialization. So in this example, let's see. So we have several inputs, the numeric integer parameter params in 3 Boolean parameters A, B, C, so which are data inputs of the block. And there are two result, res1 and res2, two Boolean variables that are calculated by this function block. So when the init event comes to the input of the function block and activates the function block for the first time, the state machine, the execution control chart, it evaluates the transitions that are outgoing from this state. There are 3 of them, and it finds that this transition init, marked with init, is now true. So by that, it jumps to the init state and executes the init algorithm. Init algorithm sets the variables active res1 and res2 to some initial values, like active will be equal to 1, and active is an internal variable that indicates that block now is active, and then 2 output variables are set to 0. So then it jumps back to the start state. So after that, whenever the event rec is occurring, so the function block gets activated, and suppose that its input values are as shown here. So at event rec, that means that these values of inputs and internal variables make the transition from start to main equal to true, and this transition occurs and the block jumps to the main state. So in the main state, there is action that consists of the main algorithm written in ladder logic and a CNF output event. So the main algorithm makes one execution. So it takes all the input variables and evaluates results, result 1 and result 2, two output variables, after which it emits the output event and makes this res1 and res2 values available outside the function block. And in case if the qualifier is equal to 0, which means that we intend to deinitialize this function block, in parameter params is equal to 2, then this transition condition will be evaluated to true, and the function block will jump into the shut state and will execute the shut algorithm, the namesake shut algorithm, that will set the output variables as it's described in this structure called text. So by this example, we show that the algorithms can be implemented in 2 different languages, in structure text, init and shut, and in ladder logic, for example, as algorithm main. And then the CNF event again is emitted, and the res1 and res2 variables will be made available outside the function block. Okay, so now let's try to understand how long and in which order, how long does event live, and in which order events are, in which order transitions are evaluated in the basic function block. So let's take a look at this example where we have only one input event rec in addition to the initialization event in it, and we have also here qualifier QI. So what are the options for execution in this function block? As it is defined in the standard, the transitions are evaluated in the order they are declared in the textual representation of the block. So in addition to this graphical representation, there is an XML format. And in that XML format, each of these transition conditions is so if a state has several outgoing transitions, like in this example, state 0 and state 2, they have 2 and 3 outgoing transitions. Evaluation starts from the one that is positioned higher in the XML representation of this function block. So in whichever transition evaluates to true, that one is executed and the block jumps to the corresponding new state. So the XML exchange format looks like shown here. So XML is a markup language that is used often very widely in different software applications, and it's a self-explanatory form of presenting programs and any kinds of data. So here is a snapshot of just a function block interface that includes several inputs, event, and association with the data, and then event outputs of the function block and variable declaration, and so on and so forth. Okay, and another interesting question is how many times an event input can be used in evaluation of execution control chart. Like in this particular example, we see that when event rec arrives, let's say with QI equal to 3, so it can be used first time here from start to state 1, then from state 1 to state 2, and then from state 2 to state 5. In all 3 transition conditions, rec variable is included. So how many times can we evaluate it and believe that it is equal to 1 so that all these transitions will be evaluated? In NXT Studio implementation of IEC 61499, it is accepted that event variable is true. In this particular case will be used 3 times, but in the next slide I will show you the general rule. While in the standard, it's interpreted in a bit different way. So every time event is used, like it here, it's reset to 0, and then in this state it will be, the function block will be waiting for another input event to come and activate the same function block. And then again, after the transition into state 2, it will be again idle and waiting until once more event rec will be occurring at the input, and so it's 3 times will be required in 3 event inputs to reach the state 3. So as it's shown here, T1, T2, and T3 means 3 times occurrence of the input event rec. So in NXT Studio, it's been implemented such a model where evaluation of ACC, execution control chart, stops when there are no enabled transition conditions anymore. So we are in the state and there are no transition conditions which are true on the outgoing arcs from that state, or the same state has been visited twice. So if we made a circle and again come to the same state, and then the event input will be reset. Like in this case, it's shown that init arrives, so the block will jump here. Then this is just a Boolean variable, so the block will transition to state 1. Then again init, and this will be used without waiting for init to come second time. And then finally it will go back to the start. But actually that was initial implementation of ECC execution logic in NXT control software, but later it was corrected so that the version that is defined in the standard now made default one. Okay. So now let's take a look at a very simple example of a basic function block that adds 2 variables, 2 real numbers, x and y. So in the software tool by NXT control, so this block is implemented as you can see here with input event rec, output event CNF, and XY inputs and out as output. So the variables are defined in the interface pane. So in the project tree, here is a section basic. Here we define this x plus y function block, and then it will open the interface. So we'll enter interface, and the graphical representation will be shown on this graphical panel on the right side. So the ECC has just one algorithm, and this algorithm rec, we will write in structured text as out equal to x plus y. So it's shown here. It's very simple ECC with 2 states, start, rec, and 2 transitions between start and rec. 1 action associated with rec algorithm, 1 algorithm, 1 action associated with rec state, and 1 algorithm in that action, and 1 CNF output event, indicating that value is the sum of x and y is calculated. Okay. So when we run, we can run this function block in the debugging mode, and then we can just enter x and y variables here in this debug mode, and we click on event imitating arrival of an input event rec to that function block, and as a result we will see the output. Like here we entered 5 and 4 inputs equal in values of x and y. We hit the rec, and we see that CNF event occurred, indicated by dot here, and the value out is now 9. So which is correct value. So, and now let's see how we could extend this function block by adding one more function to it, and that one more function will be the subtraction. So subtraction will be calculated as yet another output. Here we have add output and sub output. So we will add this and rename add out, rename the out variable, and we add one more output variable, sub out. We will add one more output event, sub OE, and we will extend our execution control chart with one more state, that state where we will do subtraction. So there will be two operating modes for this function block, one operating mode doing addition and the other operating mode doing subtraction. So the second algorithm sub will be containing this called sub variable equal to sub output equal to x minus y, while the other will be x plus y. And in the tool, when we run that function block in the debug mode, we again will be able to see that its output for the subtraction works correctly. So if we for input values 10 and 7, x and y, if we hit the sub event, then we will see that the result is 10 minus 7 is equal to 3. So this way we could be extending and adding different operating modes to existing function blocks by just adding more states and more input events. So with that, that concludes our overview of basic function blocks. And you should be already confident in taking the tool and designing simple blocks like the one shown in the lesson.